In our last video, we looked at some addition reactions of dienes, which are essentially analogous to addition reactions of alkenes. In this video, we're going to take a look at a reaction that is special to dienes called the Diels-Alder reaction. Now, one of the earliest reports of the Diels-Alder reaction is from 1926. And so in this reaction, we have a diene, a conjugated diene, reacting with another species that is called a dienophile, and it gives a cyclic product that looks like this. This is a special reaction. It is a pericyclic reaction. So it's not going through a radical mechanism, it's not going through a polar mechanism, it is going through a pericyclic mechanism, which has a cyclic transition state. This reaction in particular is a subset of pericyclic reactions called cycloaddition. We're thinking about this as a cyclic transition state, so we can imagine that these electrons move here, these electrons move here, and these electrons move here. Now, we're allowed to point to the space where the bond is going to be. It doesn't matter whether we're going clockwise or counterclockwise, as long as our electrons are moving in a circle. So, if we think about the transition state, we are starting to form bonds. This double bond is breaking. We're starting to form a new sigma bond. This bond is breaking, this bond is forming, this bond is breaking, and this sigma bond is forming. So this is our transition state, and then it leads to this product. Notice, we are breaking 3 pi bonds, we are making 1 new pi bond and 2 sigma bonds. So the net change is a loss of 2 pi bonds and a gain of 2 sigma bonds. Sigma bonds are stronger than pi bonds, so overall this is a really favorable reaction. Now we're going to see this carried out on a number of different dienes and dienophiles. So another way that you can try to focus on the reaction is to identify the ends of the diene and the ends of the dienophile, and then draw in some dotted lines to remind you that these are the carbons that are going to become connected. Now, even though this reaction is almost 100 years old, it is still a very, very useful reaction. The last time I looked in 2017, here's this really cool example of a Diels-Alder reaction. This is the diene, and this is the dienophile. And so the new 6-membered ring is this one here. So we've got the blue carbons and the red carbons, so this was the diene and dienophile, and then the black, those are the new sigma bonds that were formed. And so this Diels-Alder reaction was an important step in the total synthesis of this particular compound. The Diels-Alder reaction is a very powerful reaction because it gives us 2 new sigma bonds and up to 4 chirality centers. And our product has an alkene, which means we can carry out additional reactions. The reaction also happens with regioselectivity and stereoselectivity. So there's a lot of control that is possible in this reaction. Now here we have a few more examples of Diels-Alder reactions. And keep in mind there's a couple different ways to think about it. Once you identify the ends of the diene and the ends of the dienophile, you can draw a dotted line between them to remind you that that's where the new bonds are going to form. That's how they're going to become connected. Or you can think about the electron movement, and so these electrons move here, these electrons move here, and these electrons move here. And remember, what you get is a new 6-membered ring with a double bond over here, and in this case we have the aldehyde connected to this carbon. This is a chirality center, and we're not going to get into the details, but there is some stereoselectivity so that it's possible to predict which isomer is going to be the major product. So notice this and this, these are the new sigma bonds that are formed. In our next example, we can think about these are the bonds that are going to form, and we can imagine the electrons moving like this to give us our product that looks like this, where this is a new bond, and this is a new bond, and this is a new pi bond. In the next example, our diene to our dienophile, this time our dienophile is an alkyne instead of an alkene. But if we look, imagine these electrons move here. Now we have two pi bonds. One of them moves here, and then this one moves here. So we still get our six-membered ring with a pi bond over on the left, but because we had an alkyne, we still have one pi bond over on the right. This is connected to an ester, and this one is still connected to an ester. And one more example, we have an excess of the diene, and if you look closely at the dienophile, well, here is an alkene that can react, but also this is an alkene that react. So the fact that we have an excess means we can do the reaction on both sides. So new bonds can form here and here. Or we could think about it as these electrons move here, these go here, and these go here, while these electrons go here, here, and here, giving us, so this was our dienophile, which reacted with one diene and with another diene. In this case, we're also making 4 chirality centers, but there is selectivity within this reaction, and so we don't get a complete mess. So with the examples I have here, I just wanted to show you that this reaction works with a variety of different dienes and a variety of different dienophiles, right? So here we have butadiene, but here we have substituents on the butadiene. Here we have just ethylene, but we can also have substituents on our alkene. We can have multiple alkenes. We can have alkynes as well. So there's a lot of flexibility possible for the Diels-Alder reaction. Here we have a few more examples, and notice we are starting with the same diene, and the dienophile has the same substituents, but the top one is cis and the bottom one is trans. So we can draw our lines to focus on which atoms become connected together, or we can draw our arrows, or we can do both. And what we get here is this double bond, and then we're going to have the ester like this. So when we start out that our substituents on the dienophile are cis, we end up with our substituents cis. So from cis starting material, we get cis product. In the second example, we're starting out with trans, and this one's a little bit harder to draw the arrows just because of how the two compounds are written. But here what we're going to get looks like this, and this one will be up, while this one will be back. So from the trans starting material, we get the trans product. So this is a stereospecific reaction. Now keep in mind, stereoselectivity means that a reaction could happen to give different stereoisomers, but there's a preference for one of them. Stereospecific does not mean that it is completely stereoselective. Stereospecific means from stereoisomeric starting materials, you get stereoisomeric products. So this reaction is stereospecific. All right, so here we are making two chirality centers, but because here we're starting out cis, we end up with cis, right? So we don't have a terrible mixture. We know what we're going to get. Now this reaction is also stereoselective, and there's a difference in the way the dienophile approaches the diene, but that goes beyond what we're going to cover in 106, so you don't have to worry about that. Here we have a few more examples of Diels-Alder reactions, and in this case you can see that here we have a simple diene, but our dienophile is in a ring. Here our diene is in a ring, and our dienophile just has a substituent, and in the third example both our diene and our dienophile are in a ring. So keep in mind the Diels-Alder reaction gives you a new six-membered ring. So because we already have a ring or two rings, we're always going to make one new six-membered ring. In this case, it's pretty straightforward. We can focus on where those bonds are going to be made. We can show the movement of electrons, and then we can draw our product. So here's our new six-membered ring. And then this was the ring that originally existed. Now notice, we might not think of it this way because it's in a ring, but if we just look at this alkene, what we can see is that both substituents are on the same side. So this is cis to begin with, which means it will be cis in the product. In the next example, focus on the ends of the diene. So this carbon is going to become connected to this carbon of the dienophile, and this carbon is going to become connected to the other end of the dienophile. Okay, so this carbon does not get directly involved. All right, these carbons, they're involved in the reaction, but this is not where the new bond is formed. Okay, the new bond is formed at the ends of the diene. So when you think about where those electrons are going, you can imagine these electrons move here, these move here, and these move here. Now this carbon here, let me fill in. So here we have a CH2 group. I like to think about kind of folding that up and out of the way so that I can focus on the six-membered ring. So here is that six-membered ring that forms. We still have our aldehyde present, so new chirality center, and then don't forget we have that CH2 group that we can think of as just kind of bent up out of the way. If we were to look at this from the side, okay, this would be a bridge on top of the six-membered ring. Now, in the bottom example, I've been doing this a long time, but still, I'm not going to try to do the reaction as it's written like this. I'm going to rewrite the starting materials. So I'm going to put this one this way, but actually I'm going to go a step further, and I'm going to imagine that I fold up this carbon. I'm going to fold it up out of the way. And then I am going to redraw the dienophile because I want to make it easier to see what's going on in this reaction by aligning the diene and dienophile the way they're going to react. So now I can imagine these electrons move here, these electrons move here, and these electrons move here. So that gives me this six-membered ring. But actually, right, this was from our diene. We have a double bond here, and then this is our CH2 group that's folded up out of the way. And then this was our dienophile. Because it starts out cis, it ends up cis. So we end up with three rings in our product. This is what came from our diene, this is what came from our dienophile, and these are the new bonds in black. These are the new sigma bonds that formed. So, with a Diels-Alder reaction, it is a very, very powerful reaction. It has kind of a unique mechanism. It's unique compared to the other things we've seen. It's not a polar reaction, it's not a radical reaction, it is a pericyclic reaction. And there's actually a lot of these reactions that exist. We're not going to talk about any others this semester, but in my advanced organic class, Chem 111, we're definitely going to spend time on a number of different pericyclics. So very cool stuff. But this reaction is quite powerful, right? It's not something that was introduced 100 years ago and it's totally obsolete. No, this is something that is continuing to be used, to be developed, to offer even more selectivity. And it's just a very powerful reaction and a very cool reaction too. And you get to do one later this semester in lab. So here we've looked at a number of examples of Diels-Alder reactions to try to give you an idea of the variety of dienes and dienophiles that can undergo this reaction. In the next video, we're going to take a look at some of the mechanistic details to understand more about how this reaction works.